Hello there. This is some of the physics for the proximity effect. Here is our proximity effect example. Notice we have two cables in close proximity to each other. Ha 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 ha. They both have current going in this direction, increasing and positive. When current's going in this direction for the cables, it will create a magnetic field in the counterclockwise direction, which we can tell from our friend the right-hand rule. Hello there. These magnetic fields are not just limited to the radius of the cable. They extend outwards. And so as they extend outwards, the magnitude of the magnetic field will decrease. The proximity effect has to do with these magnetic fields interfering with each other. Since they extend, they will interfere with each other. If you looked at the center of these two cables, we notice that the magnetic field is going down over here and up over here. This right cable's magnetic field will extend over here, and it will clash with this magnetic field over here. I don't know the nitty-gritty as well as in the skin effect, but the result is a net induced electric field which opposes the electric field of the main current. This means that the electric field on this portion of the cable is less than it would be if there was no proximity effect. This decrease in the electric field results in a decrease in our drift velocity. And if we remember, the N, the Q, the dA will stay the same, but our drift velocity will decrease, and therefore our current will decrease towards the center of this guy. And the exact same thing happens on the inside of this right cable. So this current will decrease, this current will decrease. If we go to the outside of the cables, this right cable's magnetic field will extend. Over here, all the arrows are pointed down. The magnetic field from the right cable supports the magnetic field from the left cable on the outside. This results in a net induced electric field that supports the main current. This means that the net electric field is greater on these outer portions than it would be if there was no proximity effect. This means that the drift velocity towards the outside increases. If the drift velocity increases and all of the other variables stay the same, which they do, the current will increase. So we find an increase of current over here and an increase of current over here. So what we're left with is the current towards the insides is smaller, the current towards the outsides is greater, which means that there is a lot more current on the outsides, which creates a heat loss towards the outsides. And this is what we do to track the proximity effect, because we want to take it into account. The last thing is that the opposite clashing supporting magnetic fields happens when we flip it around. If there's current going this way from this cable and there's current going that way from this cable, we notice that instead of clashing in the middle, they support each other in the middle. We notice that if we were to extend out again, they clash on the outside instead of supporting on the outside. This has the exact opposite effect. We find that towards the outside, we will have less current. Towards the inside, we'll have greater current. Towards the inside, we'll have greater current. Towards the outside, we'll have less current. This is the proximity effect. Thanks, y'all.